Well, good afternoon, everyone who is attending here and also who is attending on YouTube. Thank you very much for your time and thanks for joining our webinar, the 8th webinar of Emanate today. In the topic of this month, we are talking about the wind energy. So to start this webinar, I would like to give a brief presentations about what is Emanate, which is our community of the graduates of PM3E and ME3. That we created it is in February. For those who never heard about Emanates before or who watched this video wondering what about Emanates, it was created in February 2017. At the beginning, we were sharing our internship projects through webinars. And after sometimes we were thinking that probably we want to reach all the graduates from all the years. So we invited some of you guys from 2018 and from 2016 as well. So we have created Facebook and LinkedIn groups for us to keep us updated from each other. And we were hoping that from now we would want to have a bigger networking of a PM3E and ME3 group with the collaboration through newsletter, maybe, or podcasts. These are some ideas that came into our mind. Up to now, we have performed several webinars. The last one was in the month of October. It was by 2018 graduate about advanced analytics. And we have covered various subjects. So if there are other subjects that interest you, if you want to learn about something new, you can propose it to us, and probably we can find some other graduates who can present that topic for you, and also work the other way around. If you feel like you are if you can share something of a topic of interest, and you can also propose to us. And we collaborate through sharing and support, and we try also to inspire each other by giving our opinions probably on some issues. So if you go to our Facebook and LinkedIn pages, we have some posts that trying to touch various subjects. So yeah, as I said before, if you want to join us or collaborate with us, you can contribute as a webinar speakers, or you can write articles for us as well. And you can also volunteer as a podcast speakers. For the moment, we haven't found any, but once we do, then we will organize some podcasts. And also to write on the Facebook and also on LinkedIn. So yeah, don't forget, you can search Emanate on Facebook or on LinkedIn. And if you find this logo, the green logo, then that's us. So don't hesitate to join us. And today we have Novi and Siddharth. Novita is a graduate of PM3 program in 2016, and Siddharth is a graduate of MET program in 2017. And they both at the moment are working with ECN as researchers for wind energy. And we have the privilege today to hear from them the project that they have been working on with the offshore wind energy. And so the presentation will be started. First of all, thank you for being there. Thank you for willing to present your experience. And I'm gonna give the floor soon to Siddharth and then to Novi. So for whoever who is there, please remember to always mute your microphone unless you have questions. And if you have questions in between, like in before the presentation ends, feel free. So we're trying to make it as interactive as possible. And if you for those who are joining from YouTube, same thing, you can just type your questions and your comments, and then we will pass your message to the forum. Okay, then I'll give the floor to Siddharth to start.
Yeah, thanks Astu for the introduction. I'm just sharing my screen now. Please let me know if You can see it.
Yes, I can.
Okay. So, yeah, good afternoon, everyone. So, my name is Siddharth, and I'm working currently with ECN part of TNO in the offshore wind department. And ECN part of TNO is a research institute based out of the Netherlands. And we do research on various renewable energy technologies. So within the offshore wind department, I work specifically with the installation and the operation and maintenance team. And within this team, we build simulation tools, which in which we basically try to, as accurately as possible, represent the real world of installing and operating and maintaining offshore wind farms. But the topic of this webinar, at least in the first half, I thought I would share a topic that is a bit broader, which is basically on LCOE modeling, which considers all the subsystems of an offshore wind farm that relate to its capex and opex costs. So we'll be looking at some of them in a bit more detail as to what comprises the overall LCOE estimation or the evaluation of an offshore wind farm. And the second part of this webinar would be with my colleague Novita, who would discuss in more detail the installation and the O&M tools that we have. And also, please feel free to contribute in between the presentation if you have questions or comments or remarks. And yeah, we can keep this as interactive as possible. Okay, so before moving on to the LCOE, just a short introduction on the state of offshore wind farms right now in Europe. So we see that there is a lot of activity in the North Sea, and yeah, specifically like uh, off the coast of the Netherlands and Germany, we see a lot of activity and a lot of installation of offshore wind farms. And yeah, so there's about more than 4,000 wind turbines that are currently operational, installed and operational in the North Sea and around off the coast of Europe, which contributes to about almost 16 gigawatts of installed capacity. And we see also an increase in the annual offshore wind installation, according to uh, yeah the graph on the left, where we see the uh, in the year 2017 there was an installed capacity of almost 3 gigawatts that was added. And also for these offshore wind farms, we see the nominal power of these wind turbines also increasing, as you see on the graph on the right. Although the average wind turbine capacity right now is around 5 megawatts, we have seen offshore wind farms already that are operational with 8 megawatt wind turbines. And like moving forward very shortly, we'll see also the installation of much larger machines, like 10 and 12 megawatt turbines. And yeah, as you see, the size of the wind turbines are increasing. And the Bubble Bank extension offshore wind farm, which was commissioned in 2016, has 8 megawatt machines. And as I said, like in the future, we'll have 10 and 12 megawatt machines, which will have diameters much larger than, say 200 meters. And we're talking about really big structures in the future. And looking at some other trends, we see that the, let me just hide this. Yeah, we see that the trend is to basically move further out to sea now, and because the capacity of the near shore areas are now slowly being filled up. So some wind farms, even at a distance of 200 kilometers from the shore, have been consented. And given that we are moving further away from the coast, also the water depths would increase. And this has its own set of challenges, like the type of support structure that are needed and so on, which we can see going further in the presentation. And given that we're talking about the LCOE in this discussion, it's important to, besides viewing it as a renewable source, it's important to view offshore wind farms as a business. And for different stakeholders involved in the development and the maintenance of offshore wind farms, there are different sort of parameters that they would see as being most interesting. For wind farm developers, for instance, who basically invest their capex costs in offshore wind farms, they would uh, like a fast return on their investments. And for those that are in the business of daily operation and maintenance, they would like to see larger and predictable cash flows with smaller and predictable O&M costs, maintenance costs, basically. And for electricity users and for governments, ideally, we would like to see a lower environmental impact and lower prices of electricity. So, within the scope of all this, it becomes important for, especially for wind farm developers, when they're considering to build an offshore wind farm, to know what the LCOE or the levelized cost of energy of such a wind farm would be. And this is where the ECN cost model sort of tries to give an accurate representation of the LCOE of an offshore wind farm by considering various parameters like the location of the wind farm, the type of turbines that are being used in the wind farm, the number of turbines that will be in the wind farm, the layout of the wind farm, and the met ocean conditions of the location, the soil type, and various other parameters. Uh, and in the next few slides, we'll have a look at some sort of the breakdown of each of the capex and opex elements of the cost model that helps in evaluating the LCOE. So, given that the cost model is an accurate is a tool that accurately tries to determine the LCOE, there are some trade-offs to be made. More specifically, uh, in the sense that there are boundaries in terms of wind turbine or wind farm configurations that the cost model currently considers, and these are restricted to a traditional wind farm configuration. And by the term traditional, I mean that the cost model evaluates for a wind farm where the wind turbines consist of only a single rotor, only a monopile as a support structure. We'll see different types of support structures that are being used nowadays in subsequent slides. Uh, Only a rectangular or a square shaped wind farm for which the energy yield is computed by the cost model, and also in installation and maintenance, it's restricted to the use of certain types of vessels. So SOVs and CTVs are service operation and crew transfer vessels, which I'm sure Novita will be describing in greater detail later. And traditional electrical infrastructure. So, given the boundaries, the structures of the cost model is somewhat like this. So, the ultimate goal is to basically compute all the capex elements and the opex element and the energy yield. So, with the estimation of these three parameters, we would be able to compute the LCOE of a wind farm. And the capex elements uh, result from the contribution of costs for the wind turbine itself, the cost for the foundation, the costs for the installation of all the components of the wind farm, and the electrical infrastructure or the balance of plant costs. And by foundation here, I mean like all the components that are below the rotor. So that includes the tower, the transition piece, and the support structure itself or the monopile. So these three are included in the foundation costs. And now we'll see how each of them are sort of being calculated in by the cost model. Um, So the breakdown. So initially we see the wind turbine generator cost, and this is the image of the nacelle of a typical wind turbine, where we have the different components. And the way the cost model evaluates this is with engineering models and equations that have been verified against a large number of wind turbines over the years. And it basically breaks down the components of a wind turbine. As you see in the list here, the blades, the hub, the shaft, gearbox, etc. And so basically, there are engineering equations developed for each of these. Uh, and for instance, the blade mass, it is known that it depends on the rotor power density of the wind turbine and the blade length. So using this, an equation is developed to calculate the blade mass and the costs, and so on for the hub, shaft, and all the other components. Next, like we also consider the different types of foundations right now are that are used for offshore wind turbines. So we see that monopiles are by and large the most common type of foundations that are used, and this is what the cost model is sort of restricted to for the moment. But we see an increase, or we see as we move further away from the shore, the necessity to have different types of foundations also. And although the limit here says 0 to 30 meters, it's not uncommon to have monopiles for slightly higher water depths also. It could be maybe up to 35, let's say. But it is the overwhelming majority of wind turbines that use monopiles. And to estimate the foundation costs, it's important to basically consider the types of loads that act on the foundation. Uh, this so basically, how a support structure is designed is the types of uh, excitation frequencies or the dynamic loads that are applied on a support structure are considered, and these can be loads due to the components of the wind turbine. Like for instance, there is generally considered 1P and 3P kind of frequencies that are uh, that affect basically the movement of the support structure. So and 1P and 3P frequencies basically are a result of the rotation of the um, uh, as a result of the basically the rotor of the wind turbine, and also the passing of the blade in front of the tower of the wind turbine. So these result in 1P and 3P frequency loads on the wind turbine. And for a particular wind turbine with a maximum and a minimum rotor speed, we see a particular range of these 1P and 3P frequencies. Now, these are not the only frequencies that are to be considered, but while designing your support structure or the mass of the support structure or foundation, it is important to know that these ranges should be avoided. So the range between the max and min 1P and the max and 1 3P should be avoided, because if the uh, support structure's natural frequency is designed within this range, it will lead to resonance effects, which, as you know, will lead to higher amplitudes and higher displacements, and it'll lead to larger fatigues of the support structure, which will make it subject to damage much faster. So it's important to avoid these ranges and to design your support structure such that it comes either in the stiff range, or in the soft stiff, or in the soft range. Now, if you design your support structure to be in the stiff range, that means your the mass of your support structure will be quite high, because it has to be really stiff and rigid, and the bending stiffness of it should be really high. So this would have the negative effect of your support structure being really heavy, and therefore it would increase costs also. So generally, what foundation designers do is they look at the soft stiff range and they design the uh, let's say the natural frequency of their foundation within this range. Now, once you've decided on the natural frequency of your foundation, you use the Rayleigh's method to basically estimate the mass of your foundation. This is this is your natural frequency, and from this equation, you get the mass of your support structure, which is basically a capex component to your overall LCOE. And I was just wondering if there are any questions about that, or should I just keep moving on?
No, not from my side. You can carry on.
Okay. So another aspect of the overall LCOE or the capex cost of the LCOE is the electrical infrastructure or the balance of plant infrastructure of an offshore wind farm. And this basically comprises of, as you can see from the image, like array cables, which are basically the cables that are used to uh, gather the power from different turbines to an offshore substation, and export cables, which basically connect the offshore substation to the onshore substation. So, and of course, the substations itself, the offshore and the onshore. So, all these form part of the electrical infrastructure. And it's also necessary to come up with the capex cost of these components. Now, there are different factors also that can vary in this. For instance, if the wind farm is really close to the shore, then we might not, and if there are lesser number of wind turbines in the farm, then we might not need the offshore substation, high voltage substation. We can just do with array cables and the onshore substation. But generally, now that the wind farms are quite far away, we need one or maybe even two offshore substations. And the design for these export cables can either be AC or DC cables. And the choice of AC or DC also follows some, let's say, criteria. And there is already like research going on in this field as well to find the exact break even distance when AC will be more advantageous than DC. So, for instance, like DC cables have the advantage that the transmission losses are lower, and for longer distance, therefore, this will be more effective because they're ultimately more expensive than AC cables. So, as you can see from the graph, like if the transmission distance is lesser, then you would generally choose AC, and if it's higher, you would choose for a DC configuration. And there is like some sort of, you can have opinions on what this transmission distance can and should be. And if you do like a simple, even a Google search, you can see like articles where they say the break even distance of around 70 or 80 kilometers is let's say possible now. But then yeah, that also depends on the voltage of your cables and a bunch of other things. So that's your electrical sort of infrastructure costs of the LCOE. And then we come to the installation and the O&M costs. And of course, the installation cost is also a part of the CapEx. And I'll leave these two for, for to be discussed in detail later in the second half of the webinar. And so now that we have seen all the CapEx and the OpEx components, we can have a look at the energy yield or the production of the offshore wind farm. And this is done using basically for a certain location, we profile the characteristics of the wind at that particular location. So this is done using a wind rose, which is basically a frequency of occurrence of the wind uh, at each of these wind directions. So from this graph, you can see that the frequency of occurrence of wind from the southwest direction is the highest. So this is the probability. And within these directions, we have what is called a Weibull distribution, which basically gives the probability of occurrence of a particular wind speed, and that is represented by these curves. So basically, using the wind rose and the Weibull, it's possible to compute for a wind farm the overall gross energy yield. But we also have to consider the wake effects that will inevitably occur in a large in a wind farm with a large number of turbines. And the wake effect is basically the effect of the turbines which are ahead of turbines which are in the back. So the turbines in the back will have reduced energy yields, and we have internal sort of simulation tools that help to evaluate what the wake losses for these turbines at the back will be for a wind farm of a certain layout and a certain spacing between turbines. So using these wind inputs at a certain location and this internal wake model that we've developed, we can estimate the uh, net energy yield of a wind farm after considering the wake losses. And the ratio of the net energy yield and the gross energy yield would be nothing but your wind farm efficiency. And this is generally for a well designed layout around 90%. And once we have all the capex and the opex components
I'm
and
sorry.
the
I'm
yeah
sorry, Siddharth. I kind of missed it. What was the 90% again?
yeah the 90% is generally for a well designed layout of a wind farm. The efficiency. So basically, the ratio of the net energy yield and the gross energy yield is 90%, which in other words means like you would lose 10% due to wake losses.
Okay, so it means but the losses is not coming only from the wake effect, right? Or is it?
Yeah, yeah. So from the wake effect, the losses are generally around 10%, but there are
And
additional losses as well due to the failure of turbines and stuff. So those can also add to certain losses, but yeah the the influence of the wake contributes to about let's say around 10% for a large wind farm.
okay, so let's say I'm just trying to simplify. You have a 1 megawatt of if you have, of course, it's more, but if you have 1 megawatt of turbine and you run it for 365 days per year for
Hmm.
24 hours, that what around 8,800 something. So your production is gonna be 8,800 multiply megawatt multiplied
um
by 90%.
no, not exactly, because here you're not considering also the power curve. So using the wind profile that I earlier showed, so at different wind speeds the power production will be different, right? So
Yeah.
it's not always going to produce 1 megawatt.
Okay.
At lesser wind speeds, it'll be lesser than 1 megawatt. So you have to consider that as well when you're
So
estimating your energy yield.
when you say 90% of yield, how do you calculate the number of 90%?
The 90% is basically through these models that you develop for these wake losses. So
Okay.
it involves an understanding of, like, I think the wind, let's say the dynamics before and after it passes through a certain number of turbines. And
Okay. Okay. All right.
yeah,
Yeah. Thank you.
yeah. So you have the capex and the opex that are calculated, and then the economics, let's say, can of the cost model would return basically the LCOE and different other, let's say, outputs. And to view this in a sort of a graph, we have in year zero, because of the capex costs that we saw, the foundation, etc. Large value, and then the opex cost for the next few years, and using this formula with a discount rate uh, assumption. In the numerator, we have the costs, the capex, and the opex. So the units of this would either be in millions of euros or just in cost terms. And in the denominator, you would have the energy yield over the lifetime of the wind farm. And if you discount that as well, you would have the units in gigawatt hours or megawatt hours. So then if you divide them, you get the overall LCOE in either euros per megawatt hour or euro cents per kilowatt hour. And from that, you can also estimate the net present value and the other economic parameters. And just to give an example of the, let's say, a practical case, or this information is available online of this 480 megawatt wind farm. We can see the capex is in the range of almost like 1.7 billion euros, and the opex per year for a 480 megawatt wind farm comes to like 50 million euros. And yeah, these are the cost aspects of the LCOE. And yeah, also to like your earlier point, as to like the for a 480 megawatt offshore wind farm, you would, yeah, some typically have a value of like some terawatt hours per year, 2 terawatt hours per year. And assuming like either a fixed electricity price, or you could also have different models to predict the electricity price, you can come up with your benefits over this period of operating the wind farm, and then yeah, compute the LCOE by just uh, doing the ratio.
Okay, I have a question here.
Yeah.
So you're saying that the production is 1.25 to 2 terawatt hour per year,
Mhm.
and that is this number is already with the 90% of yield.
Yeah, so this is along with the wake losses and also the O&M availability. So not all turbines will always be working. Some turbines will fail and then you have to repair them and stuff. So in general, like considering all these downtime and these wake effects, you could have something like, yeah, 1.25 to 2 terawatt hours per year.
Okay, thank you.
Yeah. Yeah. And I guess like I'll probably run through these slides a bit fast because yeah, probably running out of time. So the applications of using such an LCOE evaluation could be in determining a sort of a map like this, where we can assume a standard wind farm of let's say 1 gigawatt with a certain number of turbines and a certain type of turbine, and we can place this wind farm at different points on the North Sea. And depending on each location, we will have variations for different water depths, different distances from port, and we'll have different met-ocean conditions at these locations and environmental restrictions. And for each of these points, like a map of this sort could be created, where you can have a scale from let's say 30 to 60 euros per megawatt hour, and you could color it out nicely using a GIS tool. So this is of course not indicative of such a map, but yeah, it could be developed. And I'll just maybe run quickly through these. So for these different capex elements, we can come up with ratios, or we can come up with equations where we see, for instance, the foundation cost or the substructure cost will, of course, depend on the water depth. The larger the water depth, the more expensive the foundation cost should be, because the more length it has to be. So we can run basically the cost model for a number of iterations and come up with like a polynomial equation or something like that to basically fit for a new location what the uh, for a new water depth what the cost could be. So yeah, we could do things like this. And similarly, for installation and O&M, we can identify the kind of dependencies that different locations can have. Like for installation, we can say that the distance from port will be a factor, and the wind speed will be a factor at different locations on the North Sea. And we can basically have, yeah, a polynomial fit for installation costs with respect to these parameters. And then for every location, we can estimate what the installation costs could be. And similarly for OPEX. And yeah, so other work that can also be done with an evaluation model like this is for hub island concepts. So if So now we're just generalizing that if a wind farm, 1 gigawatt wind farm, should be constructed far from shore, the installation costs would be high because the distances from port would be high. But it can also be that there could be a small island that could be created for the purpose of installation. And on this island, there could be components that can be brought on. And from here, the installation could happen. And this island could also act as a power hub for these kind of constructions of a large number of far offshore wind farms. So, yeah, the LCOE tool could be used for estimating costs in cases like these as well. And also, we could try to optimize for a minimum LCOE. So, if we want to reduce the LCOE to as low a value as possible, we could also try to optimize for it. So, in an effort like this, we would need to identify the main factors that we would like to uh, test for. And for instance, we can take a factor like wind farm power density, for instance, which is nothing but the number of wind turbines per square kilometer. And for this parameter, we could basically run a bunch of optimization cases where we evaluate the LCOE for each case. And we could come up with a final, let's say, value of wind farm power density or these input variables that results in the least LCOE. So the LCOE being used as an objective function in combination with an optimizer like a gradient based optimizer, or could be any other optimizer, could also be like a like a possible application of an LCOE evaluation tool like this. So I guess that's more or less my part. Yeah, I just wanted to give an introduction on the different aspects of LCOE, CapEx and OpEx, and also some applications of it. And I'm open to any questions that you might have before moving to the second part of the webinar.
Okay,
Yes, Siddharth, I have a question. So,
Yeah,
what is the weight losses that you have explained before? I mean, could you tell more about that? And maybe will it be the same for the big capacity of wind farm, wind turbine, and the small capacity? Because for offshore, I think mostly you have very big wind farm. Yeah, I
yeah,
think that's the question.
yeah. Thanks for the question. As you see in this this image, we see that the influence of the wind turbines that are like first in line is quite great on the wind turbines that are behind it. So basically, the flow of wind around these in front of these wind turbines that are behind are affected because of the presence of the wind turbines in front of it. So not all wind will be able to be harnessed by these wind turbines back in the line. So this is basically the effect of the wake, and there are different ways how to calculate the yeah the wake of turbines further in the line. So there are a number of factors that depend on it also. So if there are two turbines in front of a, a turbine at the back, it would have let's say higher wake effects than if it was just one turbine in front. And so the other factors that basically define the wake are also the spacing between the turbines and the layout of the turbine. So in general now, if I'm not like very sure on yeah layout optimization, the latest sort of work that's happening, but I guess the yeah rectangular and square shaped turbines are now not that popular anymore, and it's more of a staggered configuration that is being looked into, which can minimize these yeah, wake losses in the wind farm. And as you rightly pointed out, for larger, let's say, wind turbines in a wind farm, the wake effects will be much more. because yeah, you have the influence of so many different turbines on one turbine. So yeah.
Okay, thank you for the answer. In average, the losses will be around 10% for a large wind farm and the small wind farm. Is it like that?
Yeah, like, but it's just like a really like a ballpark figure. It's
Mm,
yeah. So
okay.
yeah.
Okay, thank you, Ima. Well, I have another questions, but probably this is from someone who's watching from YouTube. But probably you
Yeah.
can answer it quickly so that we can go next to the Nofis ones. And he was saying, I would like to ask whether the presenter, whether you knows, what the floating wind farms can change the capex and opex, and what are the limitations?
For floating wind farms, yeah, I think that's like the main differences, of course, will be in the cost of the foundations. So comparison between yeah the cost of the monopiles and the cost of these sort of TLPs that will be needed in a floating should be made, and also the installation costs would be different between like loading these monopiles and taking them out to the sea versus yeah doing the installation for floating foundations. But yeah, so like actually comparing them would be yeah, I'm not extremely sure which one would be higher or lower, but yeah, so the installation cost would be different and the foundation cost itself would be different. Yeah.
I think after the second part, I will just briefly touch that floating again in terms of capex and opex.
Okay.
Okay, okay, perfect. Then now you can take it over, Novi.
Okay, I'm not sure how much time that I have, so I will just try to be quick
Yeah, sorry.
as possible. So let me share my screen first. Okay. All right. Share. Now you can see my screen. Okay. Thank you very much for the opportunity. Yeah. I'm continuing the presentation of CDAR. Basically, I want to make more explanation in the installation and O&M. Okay, this is the outlook of my presentation, but I think it's just the vision. I think CDAR already told you about how we want to accurately predict the uh, different aspects of offshore wind farm, including the installation and operation and maintenance. And I will give you a quick overview of the tools that we have currently at ECN, while we're developing it, and also we provide them to the industry, also helping them to actually make the decision based on this, the results of the tools. And we will focus on two software tools, which is ECN Install for the installation and installation modeling, and ECN O&M Calculator, basically for the operation and maintenance phase. We can have discussion, or maybe if there is a time, I can also make you a short demonstration, but it depends. Yeah, this is the same that Siddharth already mentioned. We build the strategic simulation tools for optimal decision making, all for the installation, long-term O&M strategy, also failure prediction during the operation phase of the wind farm, and also the short-term decision making, or we can say daily decision making, helping the operator actually to make decisions on how to operate the wind farm. All of this is to make the availability increase and also the cost decrease, basically. So we will have a lower LCOE in total before we have the wind farm. And also in the operation phase, we also have the lower cost as possible, and we will have a more profit. Okay, this is the chart basically summarizing what we have at ECN. Some of these tools basically is also embedded in the ACN cost model that Siddharth explained before. We have the ACN install basically for the modeling the construction and installation before the operation, and also for the planning during the project feasibility and also the tendering process. We have all the tools for the operation and maintenance. It can be used for the baseline planning of the O&M and also for optimization of the different type of strategy. And this is used for the long-term decision support. Maybe it can be for whole wind farm lifetime, but also can be like for 5 years or 10 years of future phase of the wind farm. And for the daily decision making, we also have a short-term decision making support, basically to know, like, if tomorrow, if we have different failures today, what do we need to do tomorrow? The operator needs to know which team that needs to be sent to the offshore with which configuration and with which spare parts that they need to take and so on. And also we have the load monitoring support. And in future also, in the near future also, we want to develop the tool to actually model the end of design lifetime and also the commissioning. But in this presentation, I will just briefly introduce you to two tools, ACN install and ACN O&M calculator. First, for the construction and installation planning. Basically, Siddharth already mentioned, if you want to build a wind farm, the first question is, how do we do that? What kind of turbine that we need to choose, where it will be, how deep is the sea, how many turbines, and then which kind of foundations, and so on. That's why we need to have basically the planning tool to design and also to optimize different type of installation strategy, and also to basically determine the plannings, the delays, the costs, and the risk of this construction and installations of our offshore wind farm. That's also, we aim to monitor the progress during the installations. And why we want to have the installation modeling is because, as you see also in previous presentation, you have the wind turbine is getting bigger, and also it's way further in the offshore, and that's why, you know, the ships also, maybe the requirement of the ships that we need to have is also even bigger. The lifting, it will be more complex. So that's why we want to have a commercial proof of different and new and innovative installation concepts. It can be installation method. Maybe, for example, like the floating, we cannot have the floating structure. Maybe we don't put that floating structure on the ship, but we can tow them with the tugboats. Also, we can have different support structures. It can be the floating structure, it can be monopile, it can be also gravity-based foundation structure, and also different type of wind turbines. Currently the commercial one is the normal 3-blade wind turbines, but it also can be airborne wind energy, for example. And we also, if we have different type of vessels and equipment, we can also basically model them how it's influenced to the total installations operation. So this ACN install, basically considering what it does, it's a deterministic simulation tool, which we need to have the historic weather data in order to predict what will happen in the planning. And we have different type of operation that we consider based on their characteristic. It's loading, unloading, construction, assembling, the installation, and also some type of work that we can do. we consider different actors for all the operations. It can be vessels, equipment, and also technicians. And we take into account some onshore logistics, but can be you can take a note that is actually just some onshore logistic aspect, not all of them, because we don't consider the transport from the plant, the component plant, for example, to the harbor. And we consider interdependencies between the planning. I will show you how it works later. And also we consider some weather restrictions. In this case, we found that the most important that used by industry is significant wave height and average wind speed for each operation. And we also consider learning curve for each operation, because as you may know that, like, if you do repetitive task, for example, if you need to install 70 or 80 wind turbines one after the other, most probably you will have you will reduce your duration every time, because you learn from the previous operations. And then we will have the results on the installation costs, the resource utilizations, and also installation delays. This is the, how we say, is the main aspect of the tool. We need to define the inputs, and all the inputs that we...
I'm sorry, Nofi, we have Harsha who's going to ask question here.
Yeah.
Yeah, I just read on the previous slide the results. There's a P50. I would like to know what that is, please.
Okay. Right now, we actually just consider the P50 and also the average, because, you know, like, if we put if we have the, for example, the 20 years of historic weather data, so each simulation will give different results, right?
Okay.
Yeah. So for example, we define an operation of 2 hours, for example. Like, we need to install a blade for 2 hours, but then for different so maybe this is easier. Later I will explain you for that.
Okay.
Yeah. Maybe, yeah, this is yeah, after that I will explain you how does it works actually, why we have the average in the result. For the input itself, we define the wind farm, the layout, harbor that we want to use, the mid-ocean data, or in this case is a historic weather data. It can be 5 or 20 years of weather in that location, and we need to list down and also know the cost and also the availability of the vessels that we want to use, the equipment, the components, how yeah, all the turbines, all the cables, and also all the support structures that we need. Also, we can define restrictions in the time. Maybe, for example, we don't want to work during the winter time, or maybe there is a restriction during the piling of monopile. Then we need to define all the operations, how long it will take, how many technicians that we need. And from there, we group them and we make a planning, basically, which component that we want to install first. And then we will have the breakdowns of installation costs, resource utilizations, and delay. Okay, so this is how it works. Imagine this is for one year of weather data, and then remember that before we will have at least 5 to 20 years of weather data. So we have operation that we need to make. We need to install export cables, and to install export cable, we need at that 20 days, like from 1st of December to 20th of December. But then once we finish 1st of January the next year, we can start the installation of infield cables, and this operation will take 31 days, for example. So, but each operation will have some restrictions. Most prominently is the weather, actually. So, for example, you choose the ship, but the vessel, for example, like a jackup barge. I will show you what yeah, the jackup barge is basically yeah, this one, the one that you can see, for example, the jackup, or for this, in this case, is the cable laying vessel to install the cables. So there is some restrictions in the operation. For example, you cannot the vessel cannot sail more than 3-meter significant wave height, or maybe you cannot install something if your wind speed is higher than something. So this tool actually help to simulate that, if you can actually do the operation or not, and actually to put delays if you cannot. So, for example, and then I simulate for 1 year, for example. So, and then we see that you cannot actually do all the operation in one go, because you have some delays on the weather, because maybe some time your weather goes bad and your vessel cannot sail, or your vessel cannot work. So you will have the delay here. And maybe you need to go back to the harbor, and you will have also delay on the harbor. In this case, instead of finishing your work before 20th of December, then you would end up in 10th of January. Okay, so it means that if you use the same vessel, then you cannot install the infield cables starting 1st of January, because your vessel will still be occupied. Therefore, you also will have the resource delay, and all of this it will incur costs, because instead of having the vessels until 31st of January, you will have the vessels until 10th of February, for example. And for each weather data that we have, for example, for each, because maybe I didn't explain it. Yeah, every year the weather will be different. So for each year, you will have different, basically, result on the operation. Maybe 1 year you will have more delays on the compared to the other year. So that's actually what's ECN Install trying to do, to simulate the installation operations for different weather data that we have. Also because we put some restriction on the operations. Is it answering your question?
I'm sorry, which question you're referring to, Navita?
The one that the P50, the offshore average.
I think what he was going to ask is actually the concept of the definition of the P50 itself as well.
Okay. So yeah, yeah, it's a okay, because okay. So
what is exactly P50? Is there any P70 or
No, P50 will be different than average. P50 basically the probability, 50% of the time you will have the result of a certain value.
I see. 50% chances that that result.
Yeah. So that's also what we can calculate here. So when you have different result for each simulation, that you will calculate the chance of it happening.
I see. Thank you.
Okay. So, but then also in the future, we will have also different probability chance. We will have maybe P90, P95. That's also can we can add that.
Okay.
Okay. And yeah, this is
I need to interrupt because I think we can move a bit faster.
Yeah.
Yeah. Thank you.
Okay. Yeah, this is an example. So this is what I call 1 year weather data, but usually in the simulation, we will use 5 to 20 years. This is an example of 600 megawatt wind farm. It's 80 kilometer from Dutch shore. We use monopile as a foundation, and the operation will we will have first we need to prepare the seedbed, and then we install the foundation, then we install the wind turbine, we install the cables between the wind turbines, and then we need to protect the foundation with the scour protection, and then we're commissioning the wind farm. But for this example, I exclude the export cables and the OHVS of the offshore high voltage station. And then I make I made the model in the ECN install, and we found that for 600 megawatt wind farm in the Dutch 80 kilometer from the shore, for 10 megawatt, actually, I didn't mention that, the installation cost will approximately is 86 million euro. And the project will last for 8 to 9 months, and you can see actually here the schedules. So each operation will have the durations, and also they will incur some delays, because, for example, in this case, actually, it's a quite good schedule, because you can see the delays actually not so much time for each operation, maybe some days. But if you consider different type of vessels, maybe different type of support structure, maybe you will have much more expensive installation costs and also the delays. Yeah, so that's about the ECN install. We also working quite a lot with the different strategy, and also different superstructures, and also different wind turbines. For example, in this case, we work for the we are working for the to calculate the workability and also installation method for gravity-based foundation. As you can see, you don't use the heavy vessel like in this case. And then different type of foundation, the floating. Also, not only the traditional wind turbines, but also airborne wind energy, and yeah, and so on. And to answer the previous question about the floating, currently the floating foundation of the capex of the floating wind farm is still more expensive than the monopile. I think that's actually the reason behind that is more on the component cost itself of the component cost itself of the floating foundation. So right now the foundation, the monopile is quite cheap, if I can say, compared to the other support structures. But if you see here, for the floating foundation, actually you will gain some advantage, because most probably you will not you don't need to hire really expensive vessel, like a big vessel, to install the foundation. But maybe you will only need to hire like tugboats, something like that. So it will be having it will have some trade-off. Then that's this the tool is really helping us to know which aspects that's driving the cost and also the overall LCOE. Okay, and that's actually for the installations. I want to ask you here, shall I stop or shall I continue with the O&M part?
Yeah, you can continue with the O&M part. Maybe we can have another 10 minutes to cover the remaining slides.
Okay, okay.
Thank you.
Yeah, thank you. So we continue with O&M strategy design and optimization, and we do this for the mostly for planning and operation phase. Okay, as you remember before, this is the typical wind farm layout. And if you want to operate a wind farm, you will have a probability or risk that it will fail. So all the components that actually are working in the offshore wind farm will eventually will fail. Some of the failure is bigger than the others. And we call this failure chance. We call it as an annual failure frequency or failure rates. And in order to, when you have the failure, you will have the turbine off basically. And in order to, it means that you cannot produce from that turbines, and then you need to repair them. So there is two ways looking at this. There is a direct cost, which is called that we have the repair cost that we need to spend in order to make the turbines working again. But also there is another way to see it when you, okay. This one, yeah. When the turbine is not producing, it means you also lose your income, right? So you will need to also to consider that when the turbine is not working, there will be energy loss incurred to it because you need to repair that turbine, and also because basically you lost the energy that you should have been producing. So this is an example of the one of the failure rates study that is been published. If you see here, the most failure will happen in the pitch and hydraulic system of the wind turbine, and also followed by generator, gearbox, and blades. But if you see here, you will think that okay, so most probably the pitch and hydraulic system will cost me a lot of money throughout the year because I need to repair them, and my wind turbine will not produce because of these failures. But then maybe you also need to consider how much time you need to repair for each failures. For example, in this in the same study, it shows actually not the pitch and hydraulic system that will take so much time in every failures, but actually more in the bigger components like hub, the blades, and the gearbox. So in this case, considering the failure rates of a wind turbine and the downtime that it will take to repair them, then you can see actually the gearbox will cost us most money basically. But you need also to consider if we have failures and we want to repair them, then most probably we will find that we are in the offshore situation. It means that we have also harsh weather condition. We cannot actually every time it's failed that we can just go and repair them. No, because if we have some vessel or ships that can carry the technician to fix them, they also have the constraint or restrictions. And also you need to also remember that the repairing wind turbines offshore is also expensive. And yeah, therefore you have the challenging access. Sometimes when you cannot sail with your own ship, that you need to hire a different type of access, like helicopter, for example. And also it will be difficult because maybe you don't have, when you want to work on something, then maybe you also don't have the spare part that you need right away. So we basically develop our O&M knowledge in order to actually decide in advance. So before actually we're installing and also we are operating a wind farm, we should know actually what kind of strategy that we need to put in our wind farm. If, for example, this is just example, if we have a nearshore or smaller farms, most probably it's enough that we have only crew transfer vessel, that in this case you can see that maybe just carrying 12 technicians with 1.5 meter significant wave height, and they can only carry small spare parts. But then if you have further wind farm, you cannot actually use this vessel because maybe your travel time will be, I don't know, maybe 3 hours, and it will be too much for the technician actually. And also every day you will lose so much time in order just to go to the turbines. And then you also need to consider your because when you have a wind farm, most probably you will only hire a big vessel like this, the jack-up barge, when you need to replace a large component, for example, the blade or the nacelle, or maybe some component that cannot be carried with the normal ships like the crew transfer vessels. But what about if you have even far offshore, for example, 250 kilometers from the shore, like so maybe you need also to have the surface operation vessel, like Siddharth said, or mother vessel, which can actually stay offshore for example 2 or 3 weeks. Then you don't need to go back and forth to the port every day. You can just stay there, and every day or maybe every day your vessel will just go to the turbines that is failing. And all of this again, remember that the offshore wind farm as a business, that you also need to perform. That's all of these efforts actually to have the best performance that you can be. And in this case, we use the term of KPIs, and we have different KPIs for the wind farm. For example, we have the availability, how much time that your offshore wind farm can produce, and it can be based on time, and also it can be the energy that you're producing. But also it can be also based on the reliability. It means like how much failure rates of your wind turbines, and also the repair rates of the wind turbines. There's also some other indicators that is used in the industry. For example, the intervention per wind turbines, there is a restrictive number of that, and how much percentage of reactive maintenance and schedule maintenance. And all of this in order to calculate the OPEX as low as possible, and also LCOE as low as possible. So there will be a lot of decisions to make before we actually choose some strategy. If it needs to be shore-based or offshore-based, do we need multiple harbor? And then do we need to cluster our effort with the offshore, the other offshore wind farm? Do I need the helicopters to lower my cost, to increase the accessibility, and so on? Yeah, I can skip this. I think it's just yeah, there is a basically different goals of different stakeholders for the planning phase and also operation phase. Yeah, in this case, to answer all these questions, we develop, or we created actually already for some years now, is the O&M calculator, and this is currently the current version is MATLAB based, with all the information that we have for the wind farm in order to actually accurately predict the near future O&M costs. It's suitable for both the planning or also optimization. I can give you some example. I think this is more interesting. Just 5 more minutes, I think. So this is one of the study that we did. We have 6 different location in the United States. That is basically a study to find out what is the best strategy for each wind farm. As you can see, they have different characteristics, different capacity of the wind farm, different wind turbine capacity, also different type of foundation, because they have different water depth for each location. Okay, and on top of that, they also have different characteristic of the mid-oceans. Some of the location are more challenging to access, for example, and some of the location are further than the other locations. Okay, this is just a brief type of vessels that we use in our study. It can be CTV and also SOV, the service operating vessel, that can stay in the wind farm, and with also including the daughter craft. Basically, it's just the access vessel come with the SOV. So we have in between the surface effect ship, and also maybe bigger crew transfer vessel, and also helicopter. And to replace bigger component, we have different type of equipment that we require. Basically, for the wind farm that is not so deep, with the fixed structure foundation like monopile, we use jack-up barge. But for the floating, we use towing vessel. So if there is a replacement that we need to have, that instead of working on the offshore, we tow the whole system back to the port and we repair it there. And there is some other additional vessel like cable laying vessel and diving support vessel for different type of operations. And of course, there is some other challenges in different locations, because in these locations there are actually hurricanes during these periods, and in this location we have ice that occurring every year, and in here we have deeper water. So it means that we need to have the floating foundations and also replacement by towing vessels. And from this study, we conclude actually each site needs a dedicated O&M strategy. For example, for the location that is not so far from the shore, like this one, and 22 kilometer and the 30 kilometer, crew transfer vessel is enough. But for the further offshore, we need to have a ship that actually stay in the wind farm. And for the intermediate one, maybe we can have a shore-based strategy, but we need to have a bigger vessel like this one, the 70 kilometer and 102 kilometers. And for the floating, of course, we cannot deploy the jackup barge. Instead, we need to have the towing vessels. So we actually make a combination between different strategy, and this is our result based on the the lowest cost possible and also the highest availability possible. Yeah, I think I'm done. So any question?
We have one question. Well, thank you. I think this is the end of your presentation, if I'm not wrong.
Yes.
Okay, so we have questions from YouTube from Joanna. How accurate are your models so far, or how do you? Yeah, how accurate it is so far?
The I can say the accuracy of the model, it depends on the input that we introduce basically. For the like for example,
how do you know your accuracy?
Yeah. Okay. So before we how to say before we when we are developing these tools, we also validate them with the real basically operations, a real wind farm. So for example, for the ECN install, we know that the a particular wind farm will take this much time to install, and we try to recreate recreate this wind farm in the tool, and we try to see we try to actually validate them and compare them with the real wind farm.
Okay.
So the accuracy is really for this modeling tool. I think the key of the accuracy is the input itself. If you really put the how to say as close as possible your assumptions, that it will be accurate.
Okay, and we have another questions, and it can probably be answered either by Siddharth or Novita, because this is also a larger scope. Sorry, one. Okay, so do you know about the this is a bit outside of the topic, but do you know about the conflicts or negotiations among fish industry, offshore oil and gas industry, and offshore wind industry regarding the use of certain offshore areas?
I think to better moderate this question, we can say rather, how is really the land allotted for offshore wind farms? How is the conflict avoided with all the external stakeholders, and how is actually the land allotted for these farms?
Yeah, so so I think the process of at least applying for these tenders from these wind farm developers sort of goes something like this. You initially get a clearance. I mean, firstly, in-house, you basically do a bunch of studies to validate where best your wind farm can be located and what the output of that particular wind farm will be. And yeah, parallelly, you then go through a bunch of, let's say, the environmental impact assessment studies and other studies like this are done to identify whether there are potential conflicts, etc. And yeah, once all these clearances are obtained from these different bodies, let's say, yeah, the development process starts, the construction process starts. And also tying in with that question, like there was a study that was earlier done, I think this year or sometime back, to actually have an LCOE map, like the one I was earlier describing. But in that map, there was not only the contribution of the wind capex and opex cost, but also there was a contribution of like these other factors. So suppose this area was a fishing area, then there would be additional costs added to the map, etc. at that location. So yeah, there have been studies like this also done to see the overall picture while considering these other agencies.
That's interesting, actually. This kind of studies, or is it something that ACN is also doing, or we can find it online, or?
Actually, yeah, ECN was a partner in this study, but I think this was more of a confidential report
Right.
that was released. So yeah.
Okay.
But I think in order to also to answer this question, at least for Netherlands, the location of the wind farm itself, it's already determined by the government. So we have like a area that we for that standard basically.
Okay.
I just have one question added to this question, just to be sure. The wind farms that are put offshore are put in the maritime territory of the country, or they can also be put in international waters?
Well, I think that's supposed to be the yeah. If it's a Dutch offshore, this needs to be the Dutch owned territory. But for example, of course, you can have we see actually like a joint, like a sharing area between Germany, Netherlands, and also UK, and also sometimes also Belgium. So that also can happen.
Okay, thank you.
Okay. I have my personal questions. So for the LCOE, like now that you guys have done the calculation, so and for the life cycle of the offshore, let's say, I don't know how many years is the normally the lifetime of wind turbines, and what is actually the most costly factor?
Yeah, so as far as the LCOE is concerned, the most expensive is the wind turbine costs and the foundation costs. So if right now, like the assessments are for larger, let's say, wind turbines, which are 10 megawatts and above, and the costs of the turbine and the foundation are more or less, not very different, I would say. And if you consider a wind farm of about 100 turbines, then these costs are much more than the costs of, let's say, installing them and the electrical infrastructure
And maintaining them.
Yeah, and the maintaining them. Yeah. So yeah.
The cost most prominently will come from the component cost itself.
Yeah, the turbines and the support structures. And sorry, you had another question as part of that, Astu? Hello?
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 Yeah, we have some difficulties over here.
Okay.
So I was saying that you said the cost of the turbine and the cost
Of the support structures, the monopiles.
were the most expensive, even more than the cost of the maintenance.
Yeah. So the maintenance costs, typically come to tens of millions of euros per year. But the capex cost, which is like a one-time investment for all the components and the foundations, it can go beyond 1 billion for a large wind farm, which we saw like a 480 megawatt wind farm. The total capex cost was about 1.7 billion or so.
Okay, thank you. And my next question is, who are you?
It's a bit low, Astu, your voice.
Hello?
Yeah.
Is it okay now?
A little bit better, yeah.
Yeah. My next
Yeah.
question is about who are using your tool that is developed by ECN.
I think at least I can say for the ECN install and ONM calculator, I didn't explain it because it's short of time. But most it's I think it's the stakeholder like developers, the ship contractors, the wind turbine manufacturers. Yeah, basically the one that has a stake in this installation and O&M everyday operations. So
Yeah.
it's install the one that actually yeah, the one that using mostly is the ship providers, or maybe the or maybe also the component manufacturers, if they have innovations um, like different type of support structures, or maybe different type of wind turbines. But for the operation and maintenance, usually is the developers and also the turbine manufacturers. Yeah.
Okay. All right. We have another question from YouTube. Okay, this is also what is the current approach of ECN towards energy storage? She has checked in the company website that the ECN provides strategic advice, and I was wondering of their approach.
Yeah. So actually, this is a pretty big topic right now, like this concept of, say, system integration, where wind turbines not only are connected to these offshore substations and provide electricity, but also there are possibilities of looking at storage of energy and transporting it as hydrogen, basically through old oil and gas pipelines. Um, yeah, but this is like very new, and yeah, there's this topic is pretty big also in the offshore wind business, of yeah, system integration and integrating and energy storage and all this. Yeah, so it's relatively new, but yeah, there's research going on.
Okay, that's interesting.
Yeah.
And next question is moving towards that idea that energy storage should be part of the generation, or is it to be part of the transmission or distribution?
Yeah, so I think by transmission or distribution, probably you mean after reaching the grid, right? So like, yeah, it's also being considered now in the generation process, as I just explained, like with
Mhm.
yeah, wind turbines offshore
Yeah.
being connected to, like, yeah, storage devices. Yeah.
Okay. Yeah, that answers. Um, yeah, I think, and there is another question also from Harshad. What is normally, does your LCOE or your model calculates the payback?
Yeah.
If so, what is usually the payback of an offshore project?
um like, difficult to come up with an exact number, but let's say midway during the lifetime, so or slightly more than that.
So between
Yeah,
12 years.
12. Yeah, that's around that.
Okay. All right. No, for me, it has been an interesting presentation. I didn't know that the offshore wind turbine is that complicated to install and to maintain. And
Yeah, I
actually,
mean, yeah, you in from by looking at it from the outside, it seems like it should be straightforward, but then yeah, there are a lot of challenges, especially with large components that are being manufactured nowadays. So yeah.
yeah. Thank you. Well, one last question before we and Ima, do you have a question?
No, I'm good. Thank you.
So one last question before we close the session is just for our coming interns from the current or future batches. What do you feel PM3E or ME3 has prepared you for this type of job? And what percentage of your previous degree has helped you?
Okay. Um, yeah, I guess for like a considering the I mean the ME3 or the PM3 degrees, I think like the project management role within a company like ECN or an institute like ECN, certainly doing the course can benefit you if you're working in a project management capacity, because yeah, like there are a lot of projects to manage and it's quite complex. But from a like a researcher's point of view, it's definitely like ideal if you do a specific course like in say support structure design and things like that, which were not really exposed to us during our masters. So yeah, for a research role, I think a specific masters would be more beneficial. Yeah, if that answers the question.
Yeah, it answers for me.
I think it will be the same for me.
Excuse me?
I think the answer will be the same. If you're doing more project management, then it's indeed the PM3 and MA3 will be definitely beneficial with the how to manage the project. What is the budget? What is the the all this more project management related, not the content side of the research itself.
Yeah. Okay. All right. Well, I think that's the last questions. I would like to thank everyone again for being there, and especially Siddharth and Novi for being there and for sparing the time. And if you have more questions, just feel free to post it on the Facebook group and or on the LinkedIn group. And short after this, I'm going to send some surveys just to have more feedback and to improve about the following webinars. And yeah, well, I think we would close it, the webinar over here. If there is no more questions or feedback. Okay. Well, thank you, Navita. Thank you,
Thank you very
Siddharth.
much, everyone.
Okay, thank you. Bye.
Thanks a lot. Bye.